Hey guys, this is Jack Handling, and this is Lab 3 Magnetic Field of a Bar Magnet. So part 1 will be the introduction, part 2 will be experiment and the results, and part 3 will be glow script. So the purpose of this lab was to use a Biot-Savart law to study the relationship between distance and the magnitude of the magnetic field. And the other part of this experiment was to create a glow script model that gave us a visual understanding of magnetic field. So the relevant equations and concepts. The Biot-Savart law and the distance dependence equation for magnetic field were the two main equations used in this. And by the end, I'll be able to show you that by equating these two different equations, we were able to determine the magnetic dipole moment of the bar magnet. So the main results of this was that the magnetic dipole moment was 3.593 amperes per meter squared, and that n, the distance dependence, which I'll be able to show you later in the line of best fit, was minus 2.8971 meters. So the observations I had in this experiment was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and when the magnetometer moves closer to the magnet, the measured x component of the magnetic field increased. So here are my measurements. On the top right, you can see the measurements for the field on axis, both the magnetic values and the distance. Towards the bottom, you're able to see on the off-axis values perpendicular to the magnet, in both the terms of the magnetic field and of the distance. And the graph is based off of the average values for the magnetic field and distance for the on-axis values. And this line of best fit we were able to use in the next slide to determine the magnetic dipole moment of the magnet. So here are the calculations. The distance dependence we were able to find by relating the fact that the slope here is related to this equation here with n, and because of that we could find that n, the slope, is equal to minus 2.8971 meters. Likewise, for the magnetic dipole, we're able to first off see that L and K is similar to the y-intercept here, and by substituting that in, we were able to solve for K. We also made the assumption that R was 1 meter, and with these two assumptions, we are able to equate these two equations, and through this determine the magnetic dipole moment of the bar magnet, which we found to be 3.593 amperes per meter squared. So here's the glow script code. Up here is the actual making of the cylinder magnet. Here is a function for the actual magnetic field. Over here we have vectors for on-axis and perpendicular. And then over here we have all the vectors. And down here we have the vector for the 45-degree angle. So here's a glow script model. The red arrows show the magnetic field on axis. The blue arrows show the magnetic field perpendicular, and finally this cyan arrow over here shows the magnetic field at a 45-degree angle from the axis. So the two questions we need to consider are, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So I said if we had not oriented our experiment to compensate for the magnetic north, then Earth's magnetic field would have interfered with our experiment, and the addition of Earth's magnetic field to the magnet would have skewed our results. So the second question was, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurement to differ? And I said adding another magnet would have increased the magnetic field, and therefore would see more of a magnetic field influence in our experiment. So finally, the conclusions. So by using the Biot-Savart law and the distance dependence equation for magnetic field, we were able to determine the magnetic dipole moment as calculated to be 3.593 amperes per meter squared, and the distance dependence n, which was minus 2.8971 meters. This is the